remind you where we start. Well, the last thing I said. So we saw. Oh, I said, and you know that. Oh. Okay, last time I said that if you take, an elementary matrix, or the collection of all elementary matrix, but let's say one elementary matrix, E12, and I raised it to the power of L, and then I looked at the whole conjugacy class of this. So this is all conjugates of the elementary matrices, okay, in particular all of one elementary matrix, in particular all elementary matrices. We denoted the subgroup generated by them. We said this was equal to the Lth congruent subgroup. Okay, that was the main point of last talk, if you want to. But in fact, you can make it more quantitative, this statement. And in fact, so every element here can be represented as a product of conjugates of the Lth power of E12. Something more is true, which is every element is a product of at most 2,000 conjugates. Okay, so
gamma is always SL3.
So gamma is going to be SL3. Z, it's more general, the statement, but and actually, if you go outside SLN, there are more ideas that I won't going to explain. Okay, but I won't explain. So in this series of talks, gamma is SL3Z. Okay. Generalizing this to SLN is not very hard. Okay, that's the same ideas. So the claim is that already a product of at most, I don't remember the number, some constant m is gamma L. And in fact, this constant does not depend on L. The way you prove it is actually you prove that this constant does not depend on L. Okay?
You don't mean gamma, right? But it's like specific gamma elements.
Sorry? Which gamma?
The
this one?
Conjugation of each one by gamma. It's not the normal subgroup that you take there.
No, the conjugacy class. I am taking the conjugacy class. Okay, this is a weak version of what's called bounded generation.
I see.
Okay, but I like this version because it gives you can work with powers. Okay, there's a.
It's not directly comparable, right? Because you're not.
No, it's not. No. And it's not. It's weaker in one sense and stronger in another.
Why is it weaker?
What?
Why is it weaker?
Because you're taking conjugacy classes, not just the subgroup itself.
You're not allowed to take E12 to the 2L. That's not allowed.
What?
You're taking the element, or you're taking the generator.
Yeah, no, but this is not really a problem. After finitely many conjugation, you can get that after 3, maybe 2 even, conjugation, you can get all powers. Okay, that's not the issue. Okay, the issue is to get to work with powers and to get the congruent subgroup.
This m is actually number. You just don't write the number, but it's like 1,000. Yeah.
Right. Yes.
No, this number might depend on L.
What?
This number m depends.
As I wrote it, yes, but in fact it does not. Okay. I'm not going to need it, but in this lecture, but it does not. Okay. So I'm not going to prove it. This is a harder theorem. I'll just say where's the hard part of the proof, or why is it not I mean,
your theorem?
no. This is, I don't know whose theorem it is. I'm not so good on history. I read it in a paper of Dave Whitty Morris, but this is an expository paper. He attributes it to Carter and Keller and Page, but he says this is their proof of something. This is one of the lemma in their proof of something. I don't know who proved this theorem first. Okay. So let me just say so the proof strategy is very similar to the proof of the congruent subgroup property, what we did. Okay? You go through this proof, there are several steps. Right? You prove that every matrix can be multiplied from the left and from the right by elementary matrices, by conjugates of E1, 2, and make it actually a 2-by-2 matrix. Remember? So every matrix you can do row and column operations this form and get it to A, B, C, D. Right? This is no problem. And then you prove some things about these matrices, which we encoded as many case symbols. So you prove, A, B1, B2 is equal to A, B1 times A, B2. That's again not a problem. The claim is that this if I wrote here the matrix, then I can the corresponding matrix here is a product of these two matrices times some boundedly many conjugates of E1, 2 to the L. Okay? But then the last trick was, remember, we replaced AB by PB. This is again not a problem, okay, for some prime. But then we said that PB to the P minus 1 must be equal to 1. Okay? And we somehow abused this relation P minus 1 times. Okay? And this is not allowed. Okay? Because P, I cannot bound it a priori. Okay? This is the part that needs a new proof. Okay, but this is what Keller and Carter and Page do. They give a new proof that does not need raising something to the power of P minus 1.
But do prove it related with this difference.
They prove something slightly weaker. They prove that what they actually prove, they stop there. What they actually prove is that it's a finite group of size at most 24. The exponent of it's generated by one element, and this element has order at most 24. But that's enough for them. Okay, so I want to talk about. I don't want to talk about this. I want to talk about some applications of this better version of congruent subgroup property. Let's start with some notation. Pn, I'll denote by Pn of gamma the set of nth powers. Of gamma. Okay? And the claim, let me write a corollary here, of the statement that for every n there exists an m, but actually this m is it's the same m. Well, so there exists an m. You can add or not. So you can put this for every n at either side. Okay, that's the weaker version. That if you multiply the set of powers of nth powers of gamma m times, then well, it's not everything. Okay, not every element. I want to say I want to say that every element is a product of at most 500 squares, okay, or 3,000 cubes. But it's not true because maybe the squares or the cubes don't generate the whole group, okay? But whatever it is they generate in bounded number of steps.
And you know it contains gamma of n or something, right?
Right. No, that's the proof. Okay. So the proof, probably you all see it, but the claim is that Pn gamma is close to conjugation, and it contains at least the element E12 to the n. Okay, so Pn gamma, if I multiply it, let's call it M2. If I multiply it by itself m times, m from the bounded generation, I get something that contains gamma of L, which is a finite index. Okay, it might not stop here. Gamma n, yes. So someone is listening. Okay, but then, you look at the sequence Pn gamma m plus 1 and Pn gamma m plus 2, and so on. Okay? It is bounded between gamma of n and gamma. So at one point it has to stabilize. Okay? Once it's stabilized, it cannot go any further. Right? Because if every product of 3 squares is actually a product of 2 squares, then every product of 4 squares is a product of 2 squares, and so on.
You don't need more than the index.
For example, you don't need more than the index, yes.
But you wanted a bound which is independent of n, which is a bit tricky.
What? Right. Okay, so I proved this weak version. It's actually true. It's actually true independent of. So the stronger version is also true, but they don't.
So this m also does depend on n?
Yes.
But
The proof depends. Okay. What did I want to say? Okay, so so for the next result, I want to remind you a few things that you probably some of you have forgotten about logic. So I'm going to talk about the language of groups, the first order language of groups, which is, everything every first order formula you can write using, quantifiers, logical connectors, parentheses, and multiplication in a group and equality. Okay? So let me give you examples of things you can say. If you think about it, there are not so many things you can say. Okay, you can say that the group is commutative, right? For every x, for every y, x, y is equal to y times x. Okay, you can say that the group is trivial. Okay, for every x and every y, x equals to y. Okay. You cannot say that the group is finite. Okay, there is not one sentence that expresses the claim that the group is finite. Okay?
But you can say that the group is of size 5.
You can say that the group is of size 5. Yes. So very similar to this. Okay? And so if phi is a first order statement, then, and G is a group, I will write this symbol, G satisfies phi, if phi is true when you interpret it in G. Okay? And I'll say that G is elementary equivalent to H, two groups, if they satisfy the same first order sentences, statements. Okay? If G satisfies phi, if and only if H satisfies phi. Okay? And here's the theorem that I want to talk about. And it is that so this collection of first order statements of gamma determines it. Okay? So if, well, precisely if delta is a finitely generated group and delta is elementary equivalent to gamma, remember gamma is SL3Z, then delta is actually isomorphic to gamma. Okay, this is kind of first order rigidity of a group.
This is your theorem.
This is the theorem. So you should attribute it. This is it's mainly by Chen Meiri and Alex Lubotsky. Okay, any questions?
Yes, one question.
Yes.
Is it special for SL3 or?
No, we definitely know it for SLN, and we right now, spitting blood to prove it more generally. It's true for Chevalier group, for lattices, for integral points or something commensurable to integral points in split groups. Hopefully it's true. Hopefully it's true for every. Hopefully we have the technology to prove. We will have the technology to prove it for every lattice in an isotropic group. But isotropic. The Q points, the Z points of an isotropic group, but right now I claim it only for SLN. Okay. 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 So let's prove it. This is what I want to say. I'll start with a few remarks. Okay. First of all, this theorem is false. If I replace gamma by, let's say, a free group. By groups. Okay, this is a well-known, in Israel, it's famous conjecture of Tarski that was proved by Slil Sela. It actually says that every 2 non-abelian free groups are elementary equivalent. Okay. And it's also false if you remove the finite generation.
So can you give an example of a group?
No, but this is on general grounds. You always have. This is on general grounds. You always have a model which is elementary equivalent, but not. I mean, So if you remove the countability, then you can just take ultra product of gamma. Okay, but in fact there is a countable model. So in ultra product, it's not a countable group even, but there is also a countable group. You can just get a smaller model.
But can you characterize algebraically without the finite generation?
What do you mean?
What's the structure of the groups that are equivalent to?
No, I don't know. No.
So we just have a simple example for two groups which are equivalent, not that are equivalent, but simple. Like also some groups that don't specify anything, but simple without the Tarski conjecture, something very, very simple. It's not, it's never simple.
I think the Tarski conjecture makes the point that even the simplest examples now.
No, but simpler proof. Something that.
There are even examples, I think, of metabelian groups where
yes.
there are quite simple groups where this happens.
Okay.
What group?
Metabelian, I think. Definitely solvable examples exist.
Yes. Okay. I didn't know that. Let me tell you something on the positive side. It is true for if you replace gamma by a finite group. Okay, because you can say, your finite group has 5 elements. You can say there are 5 elements, and x1 up to, x5, they are all different, and their multiplication table looks like this. X1 times x3 is equal to x5, and so on. Okay, this is a first order statement, and it's not hard to see that it's true if you replace gamma by any finitely generated abelian group. Okay, so every finitely generated abelian group is a torsion times z to something. Okay, the torsion you can get rid of here. The z to the something you can separate. I'll tell you how to separate z from z squared. Okay. If you look, so twice z, all the squares, okay, this is a definable set. You can, it's given by a formula. So you can look at the quotient, okay? And z modulo twice z is a finite group, not isomorphic to z squared modulo twice z squared, okay? So you can separate these two. Okay, let's prove this theorem at least. In the case, you assume something more. You assume not only that delta is finitely generated, but it's also residually finite.
Subgroup that you can define with first order theory.
Mm-hmm.
In that case, the quotients will be isomorphic.
Yes, yes. I'll say it in a minute. Well, no, the quotients are going to be elementary equivalent. Yes, because okay, I'll say it. I'm going to need it. Suppose you can write down a formula. Formula is just like a statement, but with variables. Suppose you can write down a formula that will actually define a group, a subgroup. Okay? Then the quotient, it's going to be anyway normal, because every definable set, every set defined by a formula is invariant to all automorphisms of the group, right? In particular conjugation. So it's going to be a normal subgroup, and you can look at the quotient. Now the quotient is not definable, in this language, but nevertheless, any statement about the quotient you can lift to a statement about G, right? To say that the quotient is a billion would just mean that for every x and y, if you look at the commutator of x and y, it belongs to the kernel, belongs to the subgroup U quotient pi. Okay? So if you have if you were able to define a subgroup, then if you know all the statements that hold for the B group, you know all the statements that hold for the quotient. Okay? So, and this is what I'm going to do, basically. So step one of the proof, I'm going to show that, in fact, so if I have this delta, then the profinite completion of delta is isomorphic to the profinite completion of gamma. Okay? And it goes like this. So fix some n. Fix number n. Look at the group generated. So I claim that there is a first order formula phi of x such that let's so gamma satisfies the following first order. I'll write it in English. Any product of m nth powers is a product of m plus 1 nth power is a product of m nth powers. Okay? And therefore, delta also satisfies this. It means that the set, okay? So if you look at the set, so if phi is the statement, x is a product of m nth powers. Okay, so in logic, formulas have the same job as equations in algebraic geometry. Okay, you have a formula, you can look for solutions, all x that satisfy this solution. So we know that phi of
which theorem do we prove?
We are proving that this theorem, that if two groups, if you have a group that's elementary equivalent to gamma, then it's actually isomorphic. Okay, the first step is to show that they have the same profinite completion. Okay, they have the same finite quotients. Okay, I'll show that they have the same finite quotients of order n. Okay. So if x is a product of so if this is phi, then if you look at phi of gamma, this is the group generated by all the nth powers. Okay?
Phi of gamma is a set of solutions.
Phi of gamma is the set of all x in gamma that satisfy phi that in gamma. Okay? But also, from the same reason, phi of delta is the group generated by p and delta. Okay? But as exactly what Nick said, we know that gamma modulo this subgroup. So in particular, it's a subgroup. Okay, phi of gamma is.
You know phi of delta is a subgroup because of elementary equivalent. And then you do
Exactly, yes. Yeah, so I know that phi, so I know this statement. Okay, this statement says that phi of gamma is a group. Okay, and it holds also for delta. Okay. So as we said, every statement about this group I can lift to a statement about gamma. Okay, so therefore these two are elementary equivalent. But this is finite, okay? And therefore, this has to be finite, and they have to be isomorphic. Okay? But if you have any subgroup, any subgroup, any homomorphism, any epimorphism, right? So if f is has exponent n, then any homomorphism from from G to F for any finite group and it has exponent n, then any homomorphism from a group to G factors through this quotient. Okay? So this quotient, the G modulo the group generated by all nth powers, that every element, if you raise it to the power n, is identity. So, if you want, replace f by of size n and replace this by n factorial or something. Okay. So let me say this again. Let me summarize. Every finite quotient of gamma or of delta, okay, factors through one of them, one of these subgroups. But these subgroups are isomorphic. Okay, so the set of finite quotients is the same. Okay? So this is step one.
You didn't use residual finiteness.
Correct.
This just proves that you have the same finite functions, right?
Yes.
And then one has to still argue. Okay. There's a small argument.
I'm not done. I'm not done with the proof.
No, but that you have the same proof finite completion is formally.
It's equivalent.
It's equivalent.
Yes.
Yeah, for finitely generated per finite groups, it is equivalent.
Wait. If you're not happy about this proof, I'll give you. I'll show you what you actually proved. Here.
No,
okay?
He's worried about. You state that they have the same finite conclusion, but you just show that they have the same finite quotient.
Okay, let me. So you're right formally, but have the same finite quotients. But now I want to claim something more than that the proof finite completion is the same. I want to claim something slightly more. Okay? So fix a presentation.
By the way, Neil, do you know a group which is both finitely equivalent to gamma, but it's not gamma? I mean,
like finitely generated group.
Is it finite?
Yeah. Yeah.
Yeah, so we just need to find the profound group with finite general group with the same profound completion as this will present. So if you have a group with the same profound completion, then they will be profoundly.
Right.
That's what I asked.
Yeah, but there is a group with the same profound completion.
Right. Don't you have? Nick should know. Nick knows how to construct.
No, but the ones that like constructed with Martin, they have increasing ranks.
I see.
But I think they exist.
Yeah. This is not enough for the proof. Okay. So, but I'll show you what's. I'll show you the extra thing you need. It's almost enough to show that they have the same profinite completion, but okay, maybe I answer it differently. I started this series of lecture by giving you two groups, slight variants of SL3Z, okay, product of congruent subgroups that have the same profinite completions, but were not isomorphic. Okay. So fix a presentation. Xi with relations Ri. Okay, these are generators, these are relations to gamma. Okay? Now suppose you have some elements, let's call them gamma I. Let's Rj. Gamma I in gamma that satisfy these relations. Okay? So basically I'm constructing a homomorphism from gamma to gamma. Right? So Xi go to gamma I. Okay? So by the normal subgroup theorem, okay, every quotient of gamma, so gamma doesn't have many quotients. Then the subgroup generated by gamma I is either gamma, so I know these are this contained in the next, gamma modulo some central subgroup, or finite. What? No, it's no, not formally. Not formally, but it's true. Okay? Every normal subgroup of SL3Z is either central or cofinite, or finite in X.
No central.
And yeah, right, sorry. Even better. Sorry.
And you claim this is equal, not isomorphic.
What?
That the image is isomorphic to gamma, or the image is gamma?
Is isomorphic to gamma? No, isomorphic to gamma. Well, no, but sorry, but then if it's isomorphic to gamma, then it has to be gamma.
Yes.
What?
What are you claiming in this step?
I claim it's actually equals to gamma. Okay, this does follow from superrigidity. Okay? Because there's only one homomorphism for SL3 from SL3C to SL3C.
So you're using both superrigidity and Margulis's normal subgroup?
I'm using everything I have, yes. You just wait. You just wait. I'm going to use the theorem of Grothendieck in a minute. Okay, so gamma is either gamma or finite. Okay? But in this case, sorry, what do I want to say? But there is a bound on, so, but there is a bound on the torsion of gamma. Okay? So in this case, probably, there is a bound on the torsion of gamma. I can add a relation, or add a bunch of relation of the form, this product is not equal to 1. Okay? So after adding, not relations, but anti-relations, conditions of the form, you know, this x1, x2, x3 inverse is not equal to 1. So let's call these conditions Sj. Any, so for every gamma I in gamma that satisfy, you know, Rj and Sj, well, this implies that the subgroup generated by gamma I is the whole gamma. Okay? This is not a first order statement. I cannot say that this is this is not a first order statement. Okay? But it has consequence which is first order statement.
What's Sj?
Sj are conditions that says something like some product of xi is not equal to 1. Okay, I need to do this to ensure that the image of gamma I is large enough. Okay? So there is a bound on how big this image can be, because it's also a subgroup of gamma. Okay? So whenever I pick an element, this implies that the subgroup generated by gamma projects onto gamma modulo the nth powers. Okay? Now this is a first order statement. Okay, so gamma satisfies the following claim for every gamma I that satisfy this relation. Gamma I projects onto, okay, this is a finite group. It's enough to show that there are words, or just to give explicit words in the gamma I that cover all elements here. Okay? And therefore, delta also satisfies the same property. Okay? So what do you get? You get that whenever you can find elements delta I that satisfies Rj but not satisfies Sj, and you know that there are, because gamma has such elements, then it will project onto each of those subgroups. Okay? So the meaning of this is that you can find a homomorphism from gamma to delta that induces an isomorphism on the pro-finite completion. Okay? So it's even more stronger than what I claimed there, didn't prove. Okay? Such that that is an isomorphism. Because every finite quotient of exponent n factors through the quotient of delta. What?
Some generators of delta?
No, these are not generators of delta. These are elements in delta that satisfy the relations of right. Since they satisfy this relation, I define a homomorphism.
Gamma is finitely presented?
No, gamma is finitely presented. Yes, yes. You know this because there is the symmetric space, and the quotient is. So the symmetric space, it's a quotient. What do you want? It's a fundamental group of a manifold, of an orbifold, right? Of a finite volume orbifold. So it's finitely presented. Okay. Is it okay? A fundamental group of a manifold, of a compact manifold, is finitely presented, right? It's almost the same. I'm saying it's, but the same proof will show you that it's finitely presented. It retracts onto something compact. It doesn't need to be a manifold. Okay? So this is what you need. You need something slightly stronger, but it turns out that it's much stronger than the post-finite completions being isomorphic. You need a homomorphism that induces this. Okay? And now Grothendieck comes to the rescue. And tells you that if gamma, maybe G1 and G2, are finitely generated groups, and you have a map that induces an isomorphism, then, so it doesn't mean that they are isomorphic yet, but it means the following: any homomorphism from G2 to GLN-Z, you can restrict to a homomorphism. So Grothendieck tells you that they have the same representation theory. Every homomorphism from G2 to GLN-Z, you can restrict to a homomorphism, you can pull back to a homomorphism from G1 to GLN-Z, okay? And the claim is that this is a bijection.
Using F.
Using F, yes, the restriction along F.
This is a deep theorem? Or?
If I have 3 minutes, well, 5 minutes, okay, I'll prove it. Okay? It's a deep theorem, but
for you, 5 minutes is enough.
It's a beautiful theorem. You know, part of the reasons I'm giving this talk is because I want everyone to know about this theorem.
Do you assume that this F hat is an isomorphism or not?
Yes, I assume that this F hat is. I didn't. Maybe my handwriting didn't.
For this, you don't need residually finite.
What?
You don't need residually finite.
I don't need residually finite. I don't need residually finite. I probably don't need that G2 is finitely generated, but no, sorry, I do need the G2. I'm not sure I need G1 to be finitely generated. And this is more general. You'll see. You'll see the proof. It's a beautiful proof.
This is not true over C?
It's true over C, yes. It's true in any generality that you can think of. Okay, but let's assume this for a minute and use it. This is almost the end of the proof. Okay, we know the assumption. Okay, we know that there is an isomorphism, that there is a homomorphism inducing an isomorphism on the post-finite completions. Okay, in particular, by the way, it means that this homomorphism, since delta is residually finite, it means that this homomorphism must be an injection, right? Because if I had since gamma is residually finite, if I had two elements that go to the identity, I could separate them in some finite quotient of gamma, but I won't be able to separate their images in a finite quotient of delta. Okay. So we're halfway there. Okay. We proved that this is an injection. It's enough to prove that this is a surjection. Okay. So what do we have? They call it rho. Okay. So let's apply this theorem, but take capital N to be 3. Okay? So what do you get? We get that home of gamma into home delta into SL3Z is in bijection with home gamma SL3Z, GIL 3Z. Okay? But I have a special element here, right? SL3Z sits inside GL3Z. It's called.
Why one side write SL and the other side GL?
Did I write SL? Should write GL. It will be SL in a minute. Okay, so I have some homomorphism here. Okay, so I have gamma mapping to what do I have to say? Wait a second. Okay. So again, what does it mean? It means that this embedding of gamma into SL3Z extends to a map between delta and SL3Z. Okay, so gamma is contained in delta, it's I, and I have a map into GL3Z. Then it extends like this. Now, the image contains, it's an extension, the image contains SL3Z. Okay? And I claim it is actually equal to SL3Z. It can't be everything, because otherwise you would have a finite quotient, GL3Z modulo SL3Z, of delta, which doesn't come from gamma. Okay? So actually, yes. You have this I into SL3Z, and delta extends. So let's call
this I is rho.
This rho, sorry. Let's call this, I don't know, tau. Okay? This is the identity. Okay, so I'm writing it. I'm writing it wrong. I have gamma here. There is a map into delta, and it has an inverse. Okay? From the right, from the wrong side that we want to prove. Okay? But we know that if I pass to the finite completions, this becomes an isomorphism. Okay? And this is its inverse. This is its one-side inverse, therefore the two-sided inverse. Okay? So I know that tau is surjective. Right? I want to prove that tau is injective. Okay? But if I apply tau, here I use the fact that gamma and delta are residually finite, finally. Okay? Tau is this extension. So here you have the embedding into GLN. Okay? By Grothendieck, it extends to a map, which I call tau.
Okay, so this dotted arrow is...
This is dotted arrow, yes.
Okay, so you assume that the map from gamma, the representation is faithful of gamma.
I can prove it, that the representation is from gamma to delta? You mean?
No, to GL.
Well, this is the embedding. No, this is the embedding of SL3 inside GL3.
Okay, you take the embedding. Okay.
The embedding, yes.
Okay, not some
yes.
representation.
Yes. Okay, that's the trick. Okay, but this is injective, and this is injective. Therefore, the composition is injective, so tau must be injective. Okay. Okay, that's a proof. Okay. So since my phone didn't ring yet, we have 5 minutes. So I'll prove to you Grothendieck's theorem with 2 minutes to spare. What?
Non-residual finite delta?
If delta is not residually finite, you need to prove that it is residually finite, there is another trick, but here, the fact that this is an embedding. This is the meaning of delta being residually finite. It embeds into the profinite completion. Again, I want to prove that tau is injective. Since this is injective, sorry? Okay. No. I want to prove that rho is surjective because I know it's injective, right? But I prefer to give you the argument for tau. I know that tau is surjective, and I want to prove that it is injective.
But it doesn't really prove that delta is reasonably finite from the triangle because you have this tau already. Or did you use it?
No. If you multiply delta by something that simple infinite group, then nothing changes. This composition is the identity, yes.
Which is proof that rho is surjective.
No, this composition.
No.
You don't know.
No, this composition is the identity.
So if you have an element in
No. What happens if you could multiply delta by something?
Yeah.
So tau is one side inverse of rho, but not from the other side. Okay. What I used here is that for profinite group, if you have an inverse from one side, then it is an inverse from the other side. Okay. It's not true for discrete groups. Okay, finally, let's prove Grothendieck's theorem. This is the highlight of the lecture. Okay, it's a beautiful proof, very Grothendieck. The way you prove it is you generalize it, okay? And you prove it, you change the statement to general rings. I won't give you the proof for general rings, but I'll prove it in succession of rings, for succession of rings. Okay, so the first case is that A is a finite ring. If A is a finite ring, this is a finite group. And we know that every homomorphism of G1 extends uniquely. Right? This is the assumption that for every finite group, there is an extension. This is the assumption. Case 2 is the case where A is ZP, the p-adic integers. This is just a tower of finite rings. If you know this theorem for every of the finite quotients, then you know it for the inverse limit. Okay? Does it make sense?
So in general for profinite rings.
It would for profinite rings, yes. I want to prove the theorem for Z. Complete local rings. When you read Grothendieck, you have to, he writes it. I'm doing a service to the community, avoiding faithful flat descent. Okay, now here, this is the main point, okay? So, take limit. Now, this is the main point. So listen up. I claim that now this is true for the localization of Z outside P. You know what? No, outside P. So I take Z and add 1 over Q for every prime Q except P. Okay, I localize, this is not a finitely generated ring. I take the localization of everything but P. Okay, and the proof goes as follows. Suppose you have, so I'll talk about, so you need to prove uniqueness and existence. You need to prove first uniqueness, okay? I won't do this, I'll go to the existence, okay? So if,
You used only
what? I use only existence, but the proof of existence needs uniqueness, of course, right? So suppose you have a homomorphism from G1 to GLN ZP. Okay? It is contained in GLN ZP. The p-adic numbers contain this element. Okay? It's actually contained also in GLN C. Okay? You know you can extend this to a homomorphism from G2 to GLN ZP. Okay, again, inside GLN C. Okay, you want to prove that actually this extension, the matrices that you get are not just p-adic, the entries of the matrices are not just p-adic numbers, but are actually rational p-adic numbers. Okay? But by uniqueness, this extension, you have this extension. Take any element of any field automorphisms of C. Okay? And you have an extension, you can conjugate it, or you can apply this field automorphism. You would get another extension, but extensions are unique. Okay? So the matrices that you get, the entries of the matrices you get, should be invariant under Galois, under all field automorphisms of C. But the only elements that are invariant under all field automorphisms of C are rational. So by uniqueness, the image of G2 is contained in GLN of the rationals, but it's also contained in GLN of P, but this is GLN. Sorry, ZP. But this is GLN of the localization. Okay, the same trick works. Do I have time? Do I have one more minute?
One of all times?
What?
Time to one of all times?
No. No, G2 is finitely generated. So if you have, case 4, you have a map from G2 to GLN of Z. Okay? You can, so G1 of Z, you can extend it to a map from to GLN Z of 2. Okay? You localize it all primes except 2. But this is finitely generated. So you start with G1 and you want to extend it to G2. Sorry. But G2 is finitely generated. Okay? So it actually falls in a finitely generated ring. Okay? So this actually falls inside Z when you localized in finitely many primes. Okay? None of them is 2. Sorry. Okay? But you can also extend it, this map also extends, I can choose a different prime, for example 3. This also extends to GLN Z localized outside 3. Okay? By the uniqueness, everything sits inside GLN Q. By the uniqueness, the entries should be elements that are both here, that are three-adically integers, and here. Okay? The image of G2 sits inside the intersection, which is GLN of Z 1/5 to 1/17, and you know how to continue. Okay, that's it.
So the uniqueness part is by specific
The uniqueness, okay, I'll say the uniqueness part. The uniqueness part is because you have a homomorphism from G1. What was it? You have a homomorphism from G2 to GLN A. The image is going to be a finitely generated ring. A finitely generated ring is residually finite. Yes. This.
So can you maybe say in a word how do you avoid the residual finiteness assumption? Just
it's.
what ideas you use? I don't know.
It's a trick. What you want to show is that there is. You claim a theorem. As far as I'll tell you, it's not going to be first order, but you can make it first order. You can. You're going to say that for every G in SL3Z, there is an element that that together with G generate, but without G, it's contained in a congruent subgroup. Okay. This cannot happen if you. So it's true for delta. Now, if you take this element G from the profinite kernel, so the kernel of the map to the finite group, there isn't such. You won't be able to find such an element. Okay. So you want to find for every G there is an element H, such that together they generate, but H itself does not generate a profinite completion.
Yeah. Okay.
Let's take
Okay. Thank you.